profile guided optimization, or PGO. Sometimes they call it directed, so it becomes PDO if you call it profile directed. So there are optimizations. Some compilers offer profile directed or profile guided optimizations. What is a profile guided optimization? What is profiling? So many people have done profiling. Okay, so what's profiling?
You run the program. You run the program and you count how many times each function is called and how long the function takes, and you get statistics on which functions are worth optimizing, because which functions are hot, which if you
yes.
find if there's an if statement where it takes the true branch 99% of the time, you can optimize for that case.
Okay, and in that case, that will correspond to thinking of the branch as creating two basic blocks. That will tell you the basic block execution frequency. So if you have an if condition, do X else do Y, then this is going to be a basic block and this is another basic block, and that information about the probability of the condition being true or false, that can give us the basic block execution frequency. How frequently will each basic block get executed, or the probability of executing X and the probability of executing Y. So it could be, for example, that 90% of the time the condition is true and we execute X, and 10% of the time the condition is not true and we execute Y. So yes, profiling is gathering some statistics about the program, statistics on function execution frequencies, basic block execution frequencies, and the time taken by each function. Usually, one of the most important pieces of information that we want the profiler to give us is the hot functions, the functions that the program spends most of its time in, and how much time it spends in each function. So we would like the profiler to tell us something like, function 7, the program spends 40% of its time in function 7. And it spends 32% of its time in function 13. And then function 2 is the next function in terms of hotness. Here, usually they are ordered because we care about the function that has the highest percentage of the program's execution time. Function 2, 10%. So what's the sum so far? We have 82. 82. So if we have another function like function 4 that has 6%, then we have 88 now. What does it mean? And then the program may have 1,000 functions. So this is a program that has 1,000 functions, but the profiler, we ran the program, and the profiler collected statistics, and it told us that 40% of the execution time is spent in F7, 32% in F13. This tells us that 88% of the program's execution time is in these 4 functions. So if I'm interested in optimizing the performance of this program, then I should focus on these 4 functions. So if there is a function here like F12 with 1%, right? Spending some time trying to optimize this will not do me any good. Right? Because even if I make it run in 0 time, I will gain 1%. Even if I make it run in 0 time. Of course, I will not be able to make it run in 0 time. Nothing runs in 0 time. But even if I make it run in 0 time, I will gain 1%. That's not much. I'm trying to speed up my program by a significant amount. So this is what profiling does in general. So this has nothing to do with compilers. So this, the concept of profiling here has nothing to do with compilers. But compilers do use profilers, or some compilers support profile-guided optimization. Some compilers allow you to compile a program, then profile, then compile again with profiling information. So some compilers, offer this mode of compilation where you first do a regular compile, just compile the program, then do profiling. In order to do profiling, you have to run your program. So when I say run your program, something should come to your mind. So there's an important question that comes to your mind when we say run the program.
You run it in an environment where the profiler can watch what it's doing.
Yes, so that's true. But when we run a program, there is an important choice that has to be made when you run a program.
You have to run it in with optimizations turned on?
Okay, well, this compile will have some optimizations turned on. Yes. Yeah.
You have to decide what input to give the program.
What input? Yeah, exactly. Because this could be dependent on the input, right? So if condition do X, else do Y, and this could be, for example, if certain condition, let's say call function F, else call function G. So depending on the condition, we will call function F or function G, and that can make a difference. And this condition could be true for some input, but for another input it could be false. So profiling is dependent on the input. So you have to decide what is a good input that you are interested in. Usually there are certain features of the program that are input independent. For example, if this condition is, for example, checking if a certain memory pointer is valid or invalid. So if it's valid, do something, else print an error message. So which one is expected to be true most of the time?
F.
The valid, yeah. So if this checks if pointer equals null or if pointer is not equal to null, then do the normal work. Otherwise, print some error message. So this is independent of the input. It doesn't matter what the input is. We expect this to be executed most of the time because this is the exception, right? So profiling is input dependent, and sometimes profiling information can vary depending on the input. But usually there is something that is common to all inputs, or something that is independent of the input, something like this, or something like loops. For example, a loop, when you have a loop in your program, usually that loop will get executed multiple times. So so you'll have things like this. Now, when the compiler offers this, compile, then profile, it will collect information like the hotness of a function, or how much time is spent in each function, and things like conditions, what's the probability of a condition being true or false, which can be captured by the basic block execution frequency. you know, how often each basic block, this basic block is executed compared to this basic block. Now this information can then be used by the compiler to do a more precise compile, or a compilation that will hopefully generate better code. Now, among the optimizations that we have studied, can you think of an optimization that can benefit greatly from profiling information? If done after profiling, it can benefit from that.
Function inlining?
Yes, yeah. Function inlining can benefit from profiling information. Yes, because profiling information, for example, can tell us how, well, the dynamic count of a for example, if a function is in a loop, we are calling a function. Yeah. So if we are inside a loop, one of the pieces of information that profiling can give us is an estimate of the number of times a loop is executed. You know, usually this is a piece of information that you don't know without profiling, right? But profiling can tell you, you know, how frequently a loop is executed, and how frequently a loop is executed will can impact our decision to inline or not inline a function. Usually, you know, do we inline if the loop is executed many times or a few times? So how does the number of executions affect our decision to inline this function?
If it executes many times.
Yeah.
High
So
dynamic call.
yeah, that's yeah. So if the dynamic count is high, if this function is, or if this loop is executed many times, we will be saving a lot of time by inlining this, because the function call overhead that we will be eliminating, that will be eliminated many times. If this is executed 1,000 times, we will be eliminating this 1,000 times. You know, so this will be part of the cost-benefit analysis. So this, if this loop is executed a large number of times, then the benefit from inlining will be higher. Okay, so inlining can benefit from profiling information. And what else? So not in the recent lectures, something that we have studied in previous lectures that can benefit greatly. In fact, we did something explicitly that, yeah.
Register allocation.
Yeah, register allocation, exactly. Remember the spill cost for each live range, that was dependent on the basic block execution frequency. And the basic block execution frequency can only be estimated precisely using profiling, right? So when you have multiple basic blocks, how many times will each basic block get executed? Usually the most accurate way of answering this question is to do profiling. And then, you know, it will tell us how many times each basic block will get executed. And the implications of that is that spill code, you know, will be more spilling in the least frequently executed basic blocks. So you want to put your spill code in the least frequently executed basic blocks, or if there is a live range, if there are two live ranges, one live range that only spans basic blocks with low frequencies of execution, and a live range that spans at least one basic block with a high frequency of execution. So you want to spill the live range that does not span a basic block with a high frequency of execution. So basically you want your spill code to be executed infrequently. You don't want it to be executed very frequently. So this is code that you are adding. These are loads and stores that you are adding, and you don't want them to be executed very frequently. So profile guided optimization is an option that compilers provide, and it can help sometimes. Okay. last time I talked about levels of optimization, and I thought that I wasn't clear about what these levels of optimization mean. So when you compile your program with GCC or G++ program .c or C++, and at -0, -01, -02, and -03. So these levels of optimization, -0 means that the compiler will not enable any optimizations. Okay. And -01, it means that it will enable the basic optimizations. -02 means it will enable more optimizations. So for example, -01, it could do local register allocation. At -02, it will do global register allocation. And even the same optimization, it can do it, the compiler can do it more or less aggressively. So it can do at a high optimization level, it can do the optimization more aggressively, like doing multiple iterations, more iterations. So that can also be a factor. And like I said last time, if you try these on a program, you compile them and then you run them, you will see the biggest increase in speed when you go from 0 to 01. Because suppose that if we put some numbers, if you run the program, you compile it with 0, then you run it. If it takes 100 seconds, then when you go to 01, you expect that to drop to 30 or 40. And then with 02, that will not drop much. So it may be 25 or something. And then when you go to 03, you may or may not see a benefit. So at 03, this could be 25, could be 24, and could be 26. So things could become worse. And why worse? Because compiler optimization, the compiler doesn't have precise information to always be certain that a specific optimization will improve performance. Okay, so it's when it comes to optimizations, compilers do lots of guessing, and it's okay to guess as long as that does not affect correctness, as long as optimizations are conservative. Conservative. So conservative means that if there is one statement that maybe dead code, but it's not clear whether it's dead code or not, then conservatively you cannot eliminate it. The compiler cannot eliminate it unless it's 100%. Unless it knows by 100% that it's dead code, it will not eliminate it. If it's a 99% chance, that this statement or instruction is dead code, the compiler cannot eliminate something based on 99%. It can only eliminate based on 100%. So this is what we mean by conservative. The compiler must preserve correctness, but it does not always, a compiler optimization does not always make things better or faster. Okay? So this is what what I meant by these optimization levels. Okay. So any questions? Okay. So I guess this is the this ends the material that we want to cover in this semester.